Thank you. Thank you for the introduction. My name is Daniel Gruß. We are going to talk about microarchitecture, vulnerabilities, past, present, and future. And today I'm presenting with Anders Fogh. And yeah, we presented at Black Hat before in 2016 together, and now we are on the stage together again.
So one of the things about Daniel and myself is that we really like to disagree. We disagree about a lot of things.
I don't know. I think we agree on most of the things.
I think the takeaway is that when Daniel says something, don't assume that I agree with it. And I'm pretty sure that you shouldn't assume that Daniel agrees with what I'm saying all the time.
Yeah. Let's just continue. So we structured the talk into 3 parts: past, present, and future, right? So let's start with the past.
No, let's start with a warning. We have way more material that we can present. We have put it in the slides. If you want to read the details afterwards, you can absolutely go and do that if you're interested in the subject. Otherwise, I recommend you don't try to read everything on every slide. Just try to listen, and that will probably serve you better.
And I already see that some of you are already thinking, the homework, of course, it's a professor. He gives us homework. Huh? So let's start with the past now.
Daniel, tell us about the past.
Yes, the past. So I want to talk about side channels first. Microarchitecture attacks and defenses. This started with side channels. And side channels have predated computers. Side channels always existed. In our everyday communication with other people, there are side channel queues that we use in everyday communication. It really got more scientific around the 1940s when we had the Tempest attacks. These were side channel effects observed on electronic typewriters. And then it also took off a bit more in '73 with a note on the confinement problem, where the covert channel, concept of a covert channel, was defined for the first time in a more formal way. Yeah, then of course this developed a bit further. We had this era with secure, provably secure operating systems.
Wonderful. The only thing that provable secure operating system couldn't solve was side channels.
So what did we do then? We said, basically that was in the Orange book, well, it's not a problem if the leakage rate is low enough. Another big step, I would say, was Paul Kocher's work in 1996, where he basically showed that you can use side channels to leak cryptographic keys. And this changed a lot, because now it was not just about covertly communicating through side channels, but it was about leaking secret information from a context where leaking a few bits is really, really important. You have 128 bits in a cryptographic key, maybe. Leaking those few bits gives you the entire key and the entire access to the secret communication or data.
I think after that paper came out, a lot of things happened in exactly crypto, and it is because of the threat model made it a realistic attack. But when we go up to 2014 to 2015, we see a shift in what is going on. But before we get there, my favorite crypto attack is a cache side channel attack on RSA from Colin Percival, which I think is sort of the first time where I really see people engaging on figuring out how the microarchitecture actually work instead of just doing timing and things like that. So,
but you can see that there's we're talking about decade-wise developments here. A decade of just side channel research on cryptographic targets, because we didn't have the threat models for other attacks. And this changed a bit around 2014, 2015, where a lot of research has looked at other targets also. There was the Rowhammer attack, 2015 here at Black Hat, actually. Yeah, and this one allows to change data in memory without having access to this data.
And I think sort of what you should be thinking about. This is side channels and microarchitectural vulnerabilities moving into the space of system security rather than cryptography.
Yes. Yeah, we also had cache template attacks back then. Also here, the idea is to move from cryptographic targets to general purpose computations, maybe keystroke input to a program. We also had, around this time, so our first Black Hat talk on prefetch side channel attacks. And this one, yeah, we broke KSLR with that. Maybe that's also not super critical, right?
And
discussing KSLR all the time.
There's an interesting point to that, right? This is side channel moving into the space of software exploitation.
Because leaking KSLR offsets previously was just a matter of software exploitation.
So what you're seeing is how side channels is solidifying itself as an exploitation technique.
Yes. So there was also concurrent work that also did that around the same time. There were many works breaking then KSLR. It has become kind of a standard thing that you do with a new side channel, that you break KSLR. Around the same time, also something else came up, trusted execution environments. Back then, Intel SGX, and that was a gift that kept on giving. Great. For researchers, great. Because they had this insane threat model, I would say, that they can't really hold up, which says everything can be malicious. I'm maybe exaggerating a bit here. Everything can be malicious, but the enclave will still be secure. You can compromise the hardware, the software stack, everything, and it's still secure.
And why is this so great? It's the threat model again, right? You have this threat model of a own computer. Prior to having an enclave, why care about a side channel if you can just read everything? Now, with SGX, you can't read everything, and now you have something to use side channels for.
Yes, with arbitrary code execution, even from the operating system kernel. That's great. Many works in this space. This really has fueled the research on microarchitectural attacks and defenses. One work that was also then widely publicized, Meltdown and Spectre in 2018. This was also at Black Hat in 2018. Yeah.
Daniel, what was the real game changer with Spectre and Meltdown?
Spectre and Meltdown were not side channels, also not fault attacks, but they are a kind of new attack, transient execution attacks, we called them, where the processor transiently does something and then things go wrong. But maybe we should look a bit more into the details of that. So let's look at Meltdown. Anders, what do we see here?
So what we see here is how Meltdown works in Intel processors of that generation. Basically, there's 4 units involved in Meltdown. Unit number 1 is the out-of-order unit. And the out-of-order unit is where instructions are executed out of order.
So this will be like a load operation to some virtual address in the kernel.
Correct. The OOO will trigger a load to the AGU.
All right, and then this AGU basically takes some bits of this virtual address, forwards them in some way to the level 1 cache, translates them maybe in some way, and also forwards it to the TLB, the translation look-aside buffer. And this happens in parallel.
So what the L1 does while the DTLB is trying to figure out the physical address, it identifies all cache lines for the index that it has gotten from the IPU and make them ready to be read.
Yeah, and that means you have multiple cache lines now that could be containing the data that you're looking for. So what we then have to do is basically select the right data. How does that work?
Well, first we need to wait for the DTLB to get the physical address. While the DTLB is getting the physical address, it will also figure out if there's any faults associated with this. These faults are sent back down to the OOO and mark the instruction as faulting. In the case of Meltdown, it's a supervisor fault.
But wait a second. If they are sent back to the out-of-order execution, it's called out-of-order execution for a reason, right? What happens with dependent instructions?
They will start executing once the request for a load is finished.
So that means they execute on whatever they got there, although later on a fault may be triggered.
That is correct. It was believed that the rollback made things secure. It's the same story about Spectre. Rollback isn't secure in the presence of side channels.
All right. How was Meltdown fixed?
So the first version of mitigating meltdown in hardware. It's a pretty simple idea, and it's simple for a reason, that is that the product was already in flight and you needed to intercept, so simple, that's good. What happened was that instead of just sending the physical address to the L1 cache, it also sent whether there was a fault or not. If there was a fault, the L1 would not send back the data, but 0.
So you don't get the data, but you get 0. That still leaves some side channel open, right? Not meltdown, but we are still there with a side channel. So what can we do to maybe more comprehensively mitigate this?
The more modern machines that Intel sells now prevents the execution of the dependent instructions if there's a fault.
But this is specific to meltdown, but there might also be more to do. So now modern processors have this defense in depth, right?
Right. So Intel has built a defense in depth for things like meltdown. It's called LASS, linear address space separation. The way it works is that when the AGU receives a load, it checks if it's from ring 3. If it's from ring 3 and the topmost bit is set, it will cause a fault, send the fault back down to the OOO, and it will never engage the L1 and the and the DTLB, thus masking a massive amount of complexity. So very small change with a big impact on the complexity that's going on.
Even if there is now a small bug in somewhere in this gray part, it's not executed anymore.
It's worth mentioning about LASS. It's a feature, and the reason why it's a feature is it changes the architecture. So you have to turn it on or off, how you want it. But it's there, and it gives you a separation.
Yeah. Of course, there's also other things beside meltdown and meltdown mitigations. We also had Spectre and LVI, and we don't have the time to talk about all of these attacks in full detail. So we will only just briefly cover those. For Spectre, Spectre was basically turning branch prediction around branch prediction side channels. Instead of leaking past branch decisions and the current state of the branch predictor, you were basically manipulating the branch predictor so that the victim would misspeculate. This is also possible with these meltdown variants, meltdown, foreshadow, and all the other attacks in that space. You can turn them around and let the victim work with data that it's not supposed to get. And with that, inject values, load value injection. But we can't cover all these attacks in detail, also not the mitigations, so we will continue right away with the next third of our presentation, the present. And here we are going to talk about the current state of things, and you mainly wanted to talk here about trends, right?
Right. So I have a professional interest in following all these kind of things, and I observe some trends. The activity level on sort of the crypto side channels that we talked about in the beginning is significantly down. One of the things is that these are mostly understood by now. There are guidance from vendors, and ARM and AMD has do it and do it M modes where you can switch into a mode that guarantees constant time for certain instructions. There is a notable caveat here. There has been some activity around data-dependent features. For example, Apple brought out a
value prediction,
data-dependent prefetch.
Also.
So there has been a little bit, but in general, it's significantly down. You don't see quite the number of paper that you used to see on
Yeah, of course, because people in the community also know how to secure cryptographic algorithms now. Just follow these constant time principles, basically. Yeah, the next part would be transient execution vulnerabilities. There also we see that the trend is going down in terms of how many new attacks are discovered. I think the big part of it was discovered, and yeah.
The caveat here, or an example of a caveat here, predictive store forwarding, you'll find that in both Intel and AMD CPUs, is an example of something that can cause transient execution. you'll also find that these features got shipped with switches where you can switch it off if you don't like them.
Yes. Next part would be stale data vulnerabilities. This also belongs kind of to the same category. It's still transient in most cases, where you access stale data and then something goes wrong, right? You get some value that you're not supposed to get. There we've seen a lot of microcode patches against all these stale data attacks. What's the current trend there?
The current trend is clearly down. I think some of it is because things have been found, but a lot of it is just sort of the time investment that has been put into eliminating these attacks before product is being shipped. And we have developed methods to find these relatively reliable.
I would say I'm not so sure that we are at the end of it yet. I think we found a category of attacks here that will reappear in products, right? We've seen this also in the software space. If we have a bug class, even years later, the same bugs keep reoccurring.
I think that's unfortunately going to be true, but I think we can say that the level of this happening is probably going down.
Yeah. Yeah, then we have 3 more categories here, and we won't talk about them too much in detail on this slide because we have multiple slides after that to go more into detail here. First is logical bugs. We have seen some of them, even at this conference. We've seen the Ghostwrite attack, but also Reptar and CacheWarp are notable examples here. What can we do to mitigate these?
Lots of things. But because they're so different and have all kinds of different root causes, they are a difficult class to work on as a class.
Yeah. We have physical properties. Physical properties are becoming more relevant as we are reducing the margins. We are becoming more power efficient with our processors. This maybe also has to be communicated to the software level. We are reducing the voltage margins. This also has effects on the software level if these are very small margins. And there we've seen attacks like Heartbleed recently or Collide and Power, which advanced this category. I think there we have an upwards trend, so I expect that we will see more attacks exploiting physical properties from the software in the future and also in more generic ways. Which brings us to the last one, exploitation methods.
Exploitation methods is using existing and known vulnerabilities in different ways to exploit it. And we're seeing an increase on work in that category. It's especially around the 2 variants of Spectre and the Power. And we'll be taking a very short look on one of the exploitation methods in another slide.
All right, let's talk about these in a bit more detail. Let's start with the first category that we mentioned at the bottom, logic issues. Logic issues, one notable example here was Reptar. How does Reptar work?
So Reptar basically is about instructions that have implicit rather than explicit parameters, and those are the string instructions on Intel. If you have a rex prefix that is supposed to modify the usage of parameters, the explicit parameters, in front of one of these instructions, what will happen, it should happen, is that the rex prefix just gets ignored. What really happens is, unfortunately, it ends up getting passed, and that changes a single bit. That single bit puts the UUP issue in a state where it can end up doing wrong input for UUP issues, meaning that wrong UUPs goes down the pipeline. Worst case scenario, you can have a machine check, which is basically means a denial of service. Your machine will need to reboot. The worst thing that can happen is a privilege escalation. Fortunately, there has been a microcode change that mitigates this vulnerability.
All right. Another notable example was CacheWarp. CacheWarp, we wanted to have Ray on stage here. Unfortunately, this was not possible because of visa delays, which is really, really sad. We wanted to have him on stage here. Yeah, and CacheWarp basically it works on confidential VMs, like AMD SCV in this case, and it exploits that the invalidate instruction that invalidates a cache line. There it's a logical bug that they didn't really consider the invalidation of cache lines in this context. So the attack works basically in 3 steps. The confidential virtual machine modifies a cache line. We use invalidate to drop the modification of the cache line, and then the confidential virtual machine continues with an outdated value. That's the gist of the attack. And I'm not sure why I need to sign in to confirm that I'm not a bot. I think I'm not a bot. Yeah. Anyways, let's take a look at the next one, which is Ghostwrite. Also for Ghostwrite, we won't go into the details, but it's another notable example of a logical bug. Here also, I would say it's similar to Reptar. We have some weird combination or some weird case of an instruction which maybe should not be doing what it does on this specific processor. But I won't go into the details of that. If you want to figure out more about that and have missed the talk yesterday, you can watch the recording. So please do that. Which brings us to the last example in this category of logical bugs, and that's Zenbleed. Here, you might know these register names like RAX, RBX, RCX. That's just flavor for the user. They don't exist on the lower levels, right? There we have a register file with thousands of actual registers, and the CPU uses those. And these registers also can be merged if you have the same value, and also you can zero them. If you zero them, you don't really want to overwrite the data. You just toggle a 0 bit, right? And then say, oh, the entire register is 0. And here the problem comes in if you basically misspeculate and then try to explicitly set this 0 bit by zeroing the register or parts of the register. The register will be merged. Then the speculation is, and then you relink, then you let the victim let the victim write data into it or load data into this register. Then you unroll the misspeculation, and you have access to the secret. So again, a logical bug, because during the misspeculation, this the merging happens and is not unrolled correctly. Yeah, what about exploitation techniques?
So here we just have a single example, and it's picked for a quote from Linus, because I kind of like that quote. I think it's kind of funny that the people that wrote the paper want that paper in their abstract of the paper. But basically what's going on here is that when you have a mutex, you'll typically find a conditional jump up on top of it, checking if the mutex is taken. That can speculate and bypass the mutex if it's locked, meaning that another thread can speculatively access a gadget. This is basically a Spectre v1 kind of vulnerability, and the existing methods of mitigating Spectre v1 will remain effective on something like this. It's just a different way of exploiting Spectre v1.
All right, which brings us, well, maybe one more comment here, because Spectre is really an attack technique that is becoming more useful in more contexts. We've seen this in academic works used as a standard technique almost to leak information as part of a larger attack. We've seen it in the context of race conditions here. We've seen it in the context of Rowhammer already. So it's becoming more and more a standard technique, also because Spectre, especially variant 1 through the PhD, is really something that will stay with us for some time, I would say. The physical domain in software, if we take a look at the past, we started off with mainly fingerprinting attacks before 2020. This was mainly fingerprinting attacks, no leakage of cryptographic information or other valuable secrets maybe. But this changed in 2020 with a platypus attack where we were able to leak an RSA key. This is just one example, full recovery of cryptographic keys. And this, again, changes the threat model. Fingerprinting is one threat model, but then if you want to attack crypto has the advantage that you can repeat the encryption over and over and over again and accumulate information this way. This is why crypto was interesting also for the cache attacks that we've talked about earlier, or the timing attacks that we've talked about earlier. This is the advantage. If you don't have a lot of leakage, just accumulate it over time. And this then also has been shown with the Herzbleed paper that you can do this also from a remote computer in a remote attack just by measuring time. So timing is a proxy here for the power consumption of the system.
So Daniel, you're walking around with crypto again. What could possibly be next?
General purpose. Of course, that's the next thing, and we showed that with the collide and power attack here. Andreas Kogler from my team did most of the work on this, and he was able to overwrite memory locations, and by that leak these data values in a clever attack by overwriting these memory locations in a targeted way. Yeah, so we are moving again from crypto to general purpose, but we still need a lot of measurements to leak the information. Another direction is software-based fault attacks. Initially, software-based, or in general, fault attacks previously required physical access in many cases. Rowhammer changed that a bit, but also there was another notable example, which was DVFS-based attacks. Rowhammer is still not solved. We see Rowhammer on the most recent processors of AMD and Intel. We see this on DDR4, DDR5. So this is still not solved, and it's not really clear how the future is going to look in that space. In academia, but we will talk about that later, we are already working on this, but we have to see what is practical. Clockscrew was maybe the first one on DVFS attacks. And it basically overclocked a processor and then faulted trust zone on ARM. We showed that with Plundervault. This is also possible on SGX enclaves. Again, thread model is a thing here. We couldn't be doing this without SGX because we need root privileges to change the voltage of the processor. Yeah, and there were more attacks also in this space. And I would also say the trend is still there that we will see more fault attacks on processors as these physical properties are more exposed. Let's talk a bit about mitigations. Anders, if we have all these problems in the processor, how are we going to fix them? Especially if they are out there already.
Yeah. So the first thing you really need to know about hardware is physical hardware cannot be changed in the field. There is no root cause fix.
And I thought I just need a steady hand. Huh?
Steady hand is not going to do it. There is no root cause fix in shipped hardware.
So what can we do instead? We need to do something when the product's out there, right?
Right. The way that this works is that at the design time, vendors add what is often called survivability features. Survivability feature number one is microcode. Microcode is a firmware, and it's very close to the hardware. It's super specific to the actual processor. Microcode is the most common used tool to mitigate vulnerabilities in hardware. We also use other firmwares. Here at Black Hat, there was a talk about TDX firmware. That TDX firmware is actually on GitHub. You can go in and look at it, and you will find that we have been using that to mitigate vulnerabilities as well. So
there's more. We cannot fix everything with microcode, right? Because not all the features are implemented in microcode, so we can't fix everything there.
That is correct. And one of the things that hardware vendors do is what colloquially is called chicken bits.
Chicken bits, yeah, know them.
The idea here is that at design time, you reason about what could possibly go wrong, and then you add a bit that can either disable or change the behavior of a feature.
Which is really nice, because if you can change the behavior, you can even react to attacks that you didn't even anticipate beforehand, if you have enough of those.
You need, these chicken bits are not free. You need to have a good idea about what can happen. You don't need to know what exactly is going to happen, but you need to have an idea about
which features do I want to disable.
Exactly.
Sometimes you still can't fix everything in hardware. And of course, this is one opportunity to bring up the Kaiser patch as an example, or KPTI, which we designed against Meltdown. Yeah, this was more efficient than it could have been done in hardware, right?
That I will doubt. There I will disagree.
Well, yes.
Well, for the actual platform,
the hardware that is out there.
For that platform, there was not an option for a microcode fix.
Of course, but if you bring out new processors, then of course you can do it more efficiently.
Yes,
of course.
But
not on the ones out in the
one there was no viable microcode patch.
Sometimes it's also not reasonable to mitigate issues, especially if you have leakage that accumulates over many years of constant attacks. Then if you leak, let's say, a bit per year, then maybe it's not the right idea to say, well, I want to have this 10% overhead mitigation against that, because it's not a realistic attack that we need to mitigate. Still, these attacks can be interesting, and we should take a look at them, because that's something we say in research. Attacks only get better.
I think another takeaway from these slides is that doing mitigations on existing hardware is very, very difficult. Yeah. You're playing with what you have, what you put in there. It doesn't always actually match your problems. There's a lot of working around and testing out. Yes. So it gets really hard. So moving on to preventing issues in the first place. So prevention starts before the product exists, and this is what we, among vendors, call pre-silicon. There's no silicon yet. Most of what you do in pre-silicon is either just normal reviews, or it's basically you have the code and you emulate and simulate it. It is really slow and it's cumbersome, but it is very important and very effective in many ways. There's very significant changes from what you'll do in software, where you can actually start running your program before it's completely done.
So there are limitations for this phase. What do we do then if we can't do it here?
So there's always limitation, right? The red part of the blog you can read on yourself. That's just how sort of our experiences with eliminating bugs in pre-silicon. So there is a short period of time between the first processor being produced, and it typically has defects that you have to sort of repeat on. And from that point in time up till you have a shippable chip, you have the chance of doing post-silicon things.
One example here would be, for instance, to return 0 instead of data in some place.
That could be a thing. Sometimes you can even fix things in hardware in this phase. We try to, right, the margins are small, so you don't typically do big fixes in this phase.
All right, let's maybe talk about the future at this point.
Now, let's just spend 1 second.
Okay.
There's one thing that I would like to talk about in terms of validation, and that's fuzzing. Fuzzing is a game changer on software. Our experience with it on hardware has been miserable. It does not work very well.
Because the state space is too large.
State space is too large. Coverage information comes mainly from pre-silicon, which is dead slow. We're just not seeing the ROI on fuzzing that you see on software.
All right. Let's talk a bit about the future. We still have a few minutes. And for the future, we again have to think about what we started the talk with, the term microarchitecture. What does it even mean? For microarchitecture, we are talking about an interface between two things. We have the architecture, the interface that you are using, and everything behind that is microarchitecture. And this is great because you can change the microarchitecture, improve performance without changing the interface that everyone is using. This, of course, has implications, because if the implementation behind an interface changes, then maybe also the assumptions are maybe changed, maybe the behavior is not identical anymore in the background, and maybe this can be observed through a side channel.
Yeah, sort of the reason why this is super important is that the growth of the entire compute system is basically driven from just 3 sources. And those sources are new process technology, it's UARCH improvement, and it's adaptation to new workloads.
And we need all 3, because all 3 we run into the limitations.
The latter of the 2 are a source of new vulnerabilities and at least security challenges. There needs to be validation on these kind of things.
Whereas the first might be a source of new physical properties in the software world.
Right? Because you have this thing that if you want to make compute better, you need to change these things. There is no option of saying, hey, we figured it out, we have secure computers, we'll just keep those. Right? That's not how it works, unfortunately.
Yeah. So let's talk a bit about the security, the future of microarchitecture security. On the offensive side, we will see new kinds of predictors, new data forwarding mechanisms, maybe even new speculative behaviors. The problem that we are facing there is memory is still very, very slow, and we need to speed this up, and we have caches for that reason, we have prefetchers for that reason, value prediction. All of these lead to problems, potentially, side channels. But we need them to ramp up the performance of our systems and the efficiency.
To give you an idea about the difference between memory and compute, accessing memory takes order of magnitude 100 clock cycles. Doing an addition or a multiplication is an order of 1 to 3 cycles. So we're talking about 97% of the latency on a multiplication or store from memory.
On the defensive side, maybe we also take a brief look at that.
I think the number one thing we've seen on the defensive side is just increased maturity. We're starting to figure out how all these things work. We're getting a much better and broader picture of these beasts from a security perspective.
Similar to as we also had on the software side with software exploitation, and there we also got better tooling and better techniques to mitigate these attacks.
We're starting to see the first new microarchitectural features for security. We're starting to see more configurability of security. The example is the predictive store forwarding on AMD that came out of the box with the switch. We're kind of starting to see these kind of things.
And that's something that I'm also very excited about, because this configurability really changes the game. Before, the software layer couldn't really do anything about what the hardware is doing in the background. It just has to live with that, work around it in the worst case. But with this configurability, we will be able to adjust what the processor does and how it does that. And that gives us more leverage to build secure systems.
A prediction here, you'll also see more support for software influence on these kind of things.
Yeah, we will also see new kinds of compute. We heard about GPU and NPUs. And these also will have microarchitectures. We have an interface, there will be an implementation, there is a microarchitecture behind that. And we build these things similar to our general purpose processors that we currently have. So we can expect similar side channel aspects in there.
And on the GPU side, we are starting to see various things. So the graphic here is the graphic from the leftover locals, basically data left in memory after execution on a graphic card on numerous vendors. We're seeing fingerprinting going on. I assume we'll see a continuation of that. those kind of things?
There's a big gap between academia and industry, but I think we are running out of time, so I will only briefly touch on that. In academia, we have provable defenses. In industry, sometimes it doesn't look the same way, because maybe they are also not that practical then. Yeah. And also, microarchitecture, we will see microarchitectures in microarchitectures. Yeah.
So modern processors have more embedded processors everywhere. And those processes are getting more and more powerful, including speculation and out-of-order execution. That's going to be a super interesting space to work in, super challenging as well.
So the takeaways. Side channels are here to stay, and microarchitectural attacks, side channels is a big part of that. They are here to stay, but we can manage them. We can keep them in check if we want to. We will see more aspects of microarchitecture and different kinds of issues with more diversity on the microarchitectural level. Yeah.
And that means there's plenty of hard work to go around for both offensive and defensive researchers. Daniel and myself will have a hard time in the future.
So it's a growth area, more microarchitecture security. And yeah, microarchitecture matters, so does microarchitecture security. Thanks for being here. I think I'm not sure we have time for questions. If we do, just go to the mics. Otherwise, you can see us in front of the room, and we will answer your questions then there. Thank you.
Thank you.